Welcome to this class on the physics of materials course. We have already gone through a couple of classes. We went through the range of topics we will do and the level of detail we will do it in. We also in the last class looked at a variety of properties as our first step towards the goals that we wish to accomplish in this course. We looked at the properties, we tried to understand, we tried to recognize that there were relationships between these properties, or at least there were correlations that you could say in certain cases that materials with a certain type of property would also imply that the same material would have a certain range of values for another property. So, in particular I linked the electronic conductivity to the thermal conductivity, and as I mentioned, the purpose of this one of the main themes in this course is that we wish to develop an understanding of where these properties originate from, and how is it that you can link events or specific phenomena occurring at extremely small scales, atomic level, subatomic level and so on, to something that you measure at a macroscopic level in a lab. So, this is the activity that we wish to pursue. So, in this process, as I mentioned, our intention is to develop models for materials, and I also mentioned that a model simply means that we will have a set of rules that we will expect the constituents of the material to obey, and as long as they obey those rules, we will be able to extract from our calculations what is it that what is the kind of behavior that the material will therefore display at a macroscopic level. So, this then forms the model and the implication of that model. To the extent that the model is correctly predicting those properties, we can assume that our model is reasonable. Okay. So, we use a variety of inputs to figure out if our model is reasonable, including our knowledge of other aspects of that material, and but more specifically we want the final outcome of that model to match a variety of experimental data. Then we are satisfied that it is a good model. What we will see as we progress through this course is that for specific properties we will be making fairly elaborate in-depth models. We will evaluate those models, and then to the extent that they succeed in meeting the properties or predicting the properties, we will accept those models. If they do not, we will have to go through the exercise all over again and refine those models that we have developed and develop the subsequent models. So, this is the exercise we will do, and from our very next class we will be getting into one of these models in great detail. What I will like to forewarn you about is that some of the models will take a few classes to reach their conclusion. It may take 3 or 4 classes, sometimes even 5 classes before we can develop all of the background that is required, justify the background, build the model, and then test the model and see what it has done. So, we are going to get into that kind of an elaborate exercise, where at all stages I believe you will stay comfortable with the material that we are discussing. So, that is where we will go. As a prelude to it, today what we will do is we will look at one particular property of a material, wherein we will the kind of information we will use for the material is something that you are probably already familiar with. Okay. So, you may be familiar with it in different contexts. So, we will pull that information together and say something about a particular property of a material such that, and we will do this discussion such that we can sort of finish it in a single class. This will give you an idea of the kind of process that we go through, although this is a much simpler process that we are going through today. So, but it will still give you an idea of the way in which we are correlating things and so on, and then trying to extract some information out of it. So, we will do this today and it will be a sort of a prelude to all the subsequent classes that will come. So, so this is the intent of today's class. So, as I mentioned, the properties that we highlighted last class were that any material you take could have mechanical properties, could have chemical properties, thermal properties, electronic properties, magnetic properties and optical properties. These are the major properties that we normally refer to, normally evaluate materials for. So, this is the general range of properties that we are interested in. Today we will look at a particular thermal property and see what we can understand of it. The thermal property that we are interested in today is simply the thermal expansion. Okay, so thermal expansion is what we are going to look at today. This is this is a property that most of us are familiar with even from our high school days. We are taught about thermal expansion, and there are a lot of day-to-day products which utilize the process of thermal expansion to carry out specific activities. Okay, a simple device that does this is the bimetallic strip, which you would normally see in many devices such as iron boxes, possibly certain types of kettles and so on, and maybe to some degree in a refrigerator, in a thermostat if it is designed based on a bimetallic strip, where essentially you have two different metals. So we will just say A and B. So we have two different metals, and they are capable of expanding to different degrees for the same rise in temperature. So if at a particular temperature both of them are such that their lengths are equal, and you see them in a horizontal disposition, so to speak, at some higher temperature, if A expands more than B, then you will see the sample curve like this. Okay. So we have a situation where the sample could be a straight sample, or it could be a curved sample depending on the temperature of the sample. Fine. So and if you, so this is when so this is at some temperature T naught, this is at some temperature T1 which is greater than T naught. Okay, so that is the relationship between those temperatures. That is what you will see for that sample. Fine. So so what you see is physically the sample is changing its dimensions, changing its shape, and therefore you could set up a switch based on it, wherein the circuit is complete or closed when this sample is straight, and the circuit is open or switched off effectively when the sample is bent. So this is how the thermostats of certain types work, which use this bimetallic strip. Okay, so so there are a lot of household appliances which are effectively making use of thermal expansion to satisfy the activity that they are designed for. There are also a number of places where you do not want thermal expansion. Okay, so or at least it is something that is not convenient to you. So often this happens when you have a variety of dissimilar materials which are in contact with each other, but have to maintain their dimensions so that they do not put undue stress on the neighboring material, or for example to maintain some kind of a sealing. So for example, if you have two surfaces in contact and you have a gasket between them, and there is a certain pressure applied on these two materials. So for example, you have one object here, and there is a gasket of some sort here, and there is another object here. Okay. And let us say that this gasket is ensuring the seal between these two pipes, for let us say these two are pipes. Now if you have a situation where due to temperature change, both of these are shrinking significantly during regular use. So let us say these pipes were intended for use at room temperature, but on that day for some reason the fluid flowing through it reaches minus 100 degrees C, which is significantly lower than the temperature it was designed for. And if both these pipes contract, then you will have a situation that this O-ring or this ring that is, or this gasket that is around these pipes will no longer be able to ensure a seal between the two of them. So quite simply you may have a situation where one pipe simply becomes this long and the other simply becomes this long, and suddenly this gasket is no longer able to, although this is exaggerated, it conveys the point that you may have a situation where the gasket no longer is in contact with either of the pipes, and therefore you have a leak. Okay, so there are a number of instances where thermal expansion is inconvenient for practical purposes. Okay, so like any property, there are places where it is useful and there are places where it is actually a hindrance. Also I wish to point out that most of us are familiar with materials that expand on heating. Okay, so this is something we are commonly aware of, and this is what we become exposed to early on. Just for your information sake, I also want you to be aware of the fact that there are specifically designed materials that shrink on heating. Okay, so this is an interesting phenomenon. It is simply called those kinds of materials are referred to as heat shrinks. So heat shrink material is what it is called. It has a very specific use, and I mean you can use it for a variety of things, but one specific use is to help you seal, make good contact between wires and seal that wire such that there is no possibility of an electric shock from it. These materials are typically polymer based materials, where what happens is you have a polymer in the form of a tube, okay, and it is supplied. There are various ways in which they accomplish this, but one way is that this is supplied wherein the material is still more in the monomer stage. There is not much of polymerization that has taken place, a limited amount of polymerization has taken place. Normally when a significant amount of polymerization takes place, the bonds become stronger and the the molecules move closer. As a result, often when you supply some heat, the polymerization will take place. So when you heat this tube, because polymerization takes place, all the atoms move closer to each other, and overall the dimension of this tube decreases. Okay, so suddenly you have a same tube with a much smaller diameter. So this is a heat shrink material. So what they would normally do is put a wire from one side and then make a knot between that wire and another wire. So and then that whole two wire system will be sitting inside this. And you have some joint here. Okay, so some joint between those two wires, and then you apply heat to this. Normally the kind of device they use is something similar to a hair dryer. It is not exactly a hair dryer, they have specific temperatures that they are interested in, but in general it is something very similar to a hair dryer. It puts a fair amount of hot air on this region, and simply because of the hot air present there, this tube will shrink. It will form a very tight hold on the wire on this side, and completely cover this joint that you have made. Okay, so it is a very effective way of sealing a joint between two wires. So this is one of the places where this material is used. So I just wanted to highlight the fact that there are materials that expand on heating, and there are also materials that shrink on heating, and there are specific uses for these kinds of materials. Right. So now we know of this property, we are at least aware of it in a macroscopic sense, and the way we measure it is simply we write, we have a certain temperature length L0 of the material at a temperature T0. We also have some other length LT at some other temperature TT. Okay, so we have two different lengths and two different temperatures, and so simply we have a situation where the length at temperature T is equal to the length at temperature T0. Okay, so length at L0 times this factor where L0 is still there, but alpha times delta T, where alpha is the linear coefficient of thermal expansion. Okay, so this is the linear coefficient of thermal expansion, and you are familiar with it. So we would write it in another way quite simply as okay, so L equals L0 into 1 plus alpha delta T. So that is your linear coefficient of thermal expansion, right. So now we would like to understand why thermal expansion is occurring. Okay, so for the purpose of our discussion, we will no longer be concerned with materials such as heat shrinks. We will look at the more familiar examples that we are used to, like the kinds of materials such as a metallic system and so on, or even we will, in this case we will look at an example of an ionic crystal, but in general we are looking at materials which we are which show the conventional behavior, which is that it expands on heating. Okay, so that kind of a behavior is what we will examine, and we will try to understand why that expansion is occurring. So first thing we will do is let us just consider as a concept, why should something expand on heating. The common idea that comes to mind is that when you heat, people are often aware that the atoms present in a solid vibrate. Okay, so this is something that people are aware of. If you go to 0 Kelvin, the atoms are stationary. If you really accomplish 0 Kelvin, which is I mean it is only theoretically possible, but assuming you actually reach 0 Kelvin, the atoms become frozen, they stay stationary. At any higher temperature, the manner in which the solid reaches that temperature or attains that temperature is that the atoms within that solid are now vibrating in a manner that is commensurate with that temperature. Okay, so that is one of the ways in which that material reaches that temperature. Okay, so this is what is happening. So if you raise the temperature, the amplitude with which the vibrations occur in that solid go up, right. So at some level, without realizing it, often people think that since the vibration amplitude has gone up, the material will expand. Okay, so this is the general idea that people have, that this is the reason why materials expand. Now the problem with this issue, with this situation is that when a vibration occurs, it is occurring both, if for a purpose of understanding, let us say a forward direction and a reverse direction. It is occurring both in the forward direction as well as in the reverse direction. When that happens, the mean position of that vibration is the same. So when the mean position of the vibration is the same, on average for that solid, there is no expansion that is going to occur. On average, the atoms are still going to have the same position. They are simply going to get displaced more from their position in two different directions, and they will come back to the mean position. So as long as the mean positions of the atoms remains the same, simply raising the amplitude of vibration is not going to result in expansion of the solid. This is a very fundamental concept. Okay, so you need to understand that simply raising the amplitude of vibration, and therefore simply raising the temperature which causes this rise in amplitude of vibration, cannot directly explain the expansion of a solid. Therefore we need to look deeper to understand why this expansion is occurring, and understand clearly that you cannot just explain it away by saying that amplitude has gone up of vibration. Okay, so that is the first concept that I would like you to become aware of. So therefore we will now try to build some detail into how a material functions and see if we can understand thermal expansion. To do this, we will take the example of some ionic crystal and say for example KCl or NaCl, potassium chloride or sodium chloride, and we will see how it comes together. That is our first activity. We will see how it comes together, what is the consequence of how it comes together, and then based on how it has come together, we will see what it implies with respect to thermal expansion. Okay, so this is the two-step process that we will go through today. Okay, so we will now look at this an ionic crystal, either say potassium chloride or sodium chloride, and we will see how this crystal is built up, right. So to do this, what we need to consider is the fact that in the crystal we can think of it as containing K plus ions, okay, or Na plus ions, and Cl minus ions. Okay, so when you actually get the crystal, so sodium chloride is your common salt, if you take it, it already has these ions in it, right. So for our understanding, we will step back, we will say that somehow we have separately got sodium and chlorine or chloride or chlorine separately, and then we would like to build the sodium chloride crystal. So to do that, we will do it in stages. So first we will assume that we have one atom of sodium which is available to us separately, and one atom of chlorine which is also available to us separately, and that these are infinitely separate from each other. So at this moment they are not in a position to interact with each other. Okay, so what we will do is we will take sodium, and from this we will remove one electron. okay. So I have now removed one electron from sodium, and let us say I have removed the electron and taken that electron infinitely away from the sodium original sodium atom, okay. So in this process what I have done is I have ionized this sodium atom. So corresponding to this there is a certain amount of energy I must provide to take this electron out, and that energy is referred to as ionization energy. Okay. So I have to provide ionization energy to get the electron off of the sodium atom, and that is of the order of about 5.1 electron volts, okay. So of the order of 5.1 electron volts is what I need to provide to get this electron off of the sodium atom, right. So this I have done independently, far away. By the same token, and so just to also to highlight, this is energy that I have provided externally to that system, okay. So if you wish to look at it from the perspective of the energy of the system or energy of the constituents, in this case the energy of the system has actually gone up, okay. So we will actually do calculations with respect to energy of the system. In this case the energy of the system has gone up, so by our convention we will simply say this is plus 5.1 electron volts. We will denote plus to mean that the energy has gone up, minus to mean the energy has gone down. In general the nature prefers lower energy, so we will move towards more and more negative energy to the extent that is possible, okay. So and that is in a relative sense. So we have plus 5.1 electron volts. Independently we will take chlorine, a chlorine atom, we will add an electron to it and we will create a Cl minus ion, okay. So this we will do independently. Right now these, even though I have written them next to each other, they are not related to each other. I have done these two processes independently, okay. So to do this, when you do this, there is a certain amount of energy that is released, and that we refer to as electron affinity. And in this case it is of the order of 3.7 electron volts per atom. In each of these cases I am talking of on a per atom basis, 3.7 electron volts. In this case this process is releasing that energy, okay, because it prefers to be as a Cl minus, it is releasing that energy, and therefore we would call this that reduces the energy of the system, and so we will call that as a minus 3.7 electron volts, okay. So these two things have occurred independently, right. So simply generating a sodium plus ion and a chlorine minus ion requires a net energy of plus 5.1 electron volts and minus 3.7 electron volts. So if you total this, this is about plus 1.4 electron volts, okay. So if those numbers, based on those numbers we will proceed for our purpose, because this is just a order of magnitude calculation that we are doing. What we see is we have a plus 1.4 electron volts. In other words, simply creating a sodium plus ion and a Cl minus ion and keeping them separate from each other requires us to provide a total of 1.4 electron volts. So therefore you see this is not something that is energetically favorable. Energetically favorable means the energy of the overall system should decrease. Right now it has gone up by 1.4 electron volts, right. So other processes must occur which help us to reduce the overall energy of the system, so that at the end of it all we can have a crystal which has sodium plus ions and Cl minus ions, right. So overall at that end we realize that in nature that already exists. So that means there are other processes that are occurring over and above this step that we have just discussed, which then enables you to reduce the energy of the system. So what happens is that now you have a sodium plus ion and a chlorine minus ion. The process that is occurring that helps us reduce the energy of the system is that these two attract each other, and the closer you bring them to each other, the energy of the system goes down, okay. So what we have is a plus 1.4 electron volts to create these two ions. We also have the energy due to the attraction of these ions as they move closer and closer to each other, and the fact that these are oppositely charged ions. Okay, so this is the energy that comes due to the attraction between the two ions that are oppositely charged as they move closer and closer to each other. Okay, so the decrease in energy that is occurring, energy as a function of the distance between them. So when they are infinitely apart, this energy due to the interaction between them is 0. Okay, so as you bring them closer and closer and closer, this gets going lower and lower and lower. Okay, so you get more and more negative energy proportional to 1 by r that is occurring as you bring them closer and closer and closer. So we now have a expression which tells us that the energy of the system is now going to depend on the distance between the ions. Okay, so we have done a 2-step process so far. We have taken separately created the sodium and chlorine ions, and then we have moved them together. Okay, so we have attempted to move them together. So this is the second contribution to the energy in the system. Okay. There is one other contribution to the energy of the system which we will add to this picture, which is that as you bring the ions very very close, then what happens is the inner shell electrons of the two atoms or the two ions now begin to overlap. The electron clouds of the two atoms, so to speak, or two ions, so to speak, begin to overlap. When that happens, the electrons in the inner shells are now forced to go to higher energy levels, because to avoid this issue of having this more electrons in the same energy levels and so on. So they actually end up having to go to higher energy levels, and so if you push the ions indefinitely close, a repulsion force of repulsion sets in, which tries to push these ions away, and that repulsion occurs because of the inner shell electrons which now begin to overlap with each other, okay, or the electron clouds which begin to overlap with each other, which begin to push these atoms. So we have that energy corresponding to that given by an expression which is simply where B is some constant r power n, where n is of the order of 10. Okay, so of the order of B by r, so this is B by r power 10. Okay, so this is the third contribution that we have. Okay. Now this is going to raise the energy of the system because it is going to push the electrons up to higher energy levels, therefore this is a positive contribution to the system. So if you take all of these contributions together, we now have the overall energy of the system being given as okay. So I have just corrected this last term, it is given to you in the form of electron volts. We can just convert that to joules, so therefore I have just done that correction there using 1.6 into 10 to the power minus 19, but it does not really, that is not the critical thing because that is a constant, that is all you need to remember. What you need to see is that this is a positive quantity, okay, so it is not really favoring the formation of this process of this crystal. This is a positive quantity, this also does not favor the formation of this sodium chloride crystal. This is the negative quantity, and the negative quantity, as I mentioned, means the energy of the system is being lowered, therefore this is favorable to the formation of the crystal. Okay. So we see that there is a competition between some quantities that are negative and some quantities that are positive. The crystal eventually forms and it eventually has a certain dimension etc. associated with it due to the interplay of these positive and negative quantities. So at the end of it, what happens at equilibrium is when these things balance each other out, okay, or you have the minimum, with minimum energy of the system is attained, that is when the crystal becomes stable. So we will make a small diagram using these parameters, and then we will see what the diagram tells us, right. So the diagram that we will make is simply energy as a function of the distance between the ions. Just to reiterate, r is the distance between those ions, okay, which initially starts out at infinite distance between infinity, the distance between the ions, and then you bring it closer. B is a constant in this term. In the attraction term between the ions, the charge in this case happens to be just a unit positive charge and a unit negative charge. That is why we have simply used the electron charge here, that is the small e. This epsilon naught is the permittivity of free space, which I am sure you are aware of from high school days, and this r again is the distance between the ions. Okay, so that is this term, that is this term, and then you have a constant, right. So let us make a diagram now. This is energy on your y axis, and we will have, this is r, that is r tending to infinity. Okay. So this is energy on your y axis, that is r tending to infinity, the position or the distance between the ions. Okay. So this is what we have. So there is just arbitrary units on the y axis, just it is some linear scale that we will make use of to our convenience. This is not really drawn to scale, this is to help us understand what is happening, right. So when you are at infinity, this term here is 0, r is infinity, therefore this is 0. This term here is also 0 because r is infinity. Okay. So the only term you have is this constant term, which is what we originally calculated, right. So we will, and we see that that is some kind of a positive constant, so we will just put some positive mark here. Okay. So and we will just say that that is that 1.4 into 1.6 into 10 to the power minus 19, right. And if you just look at it term by term, this last term is independent of r, there is no r value there, therefore it is independent of r, therefore regardless of the position of these two ions, the contribution of that term is the same. Okay. So I am going to plot here the contribution of each term independently, and then we will sum up those terms, which will give you this total term here or this total expression here, right. So independently we will do it first and then we will total it up. So if you take it independently, the last term there is independent of position, and therefore at all values of r the last term's contribution is the same. Okay. So this dotted line here shows you the contribution of the last term, which is now independent of position. Okay. So that is what this is. The first term, if we take, is a negative term, but at r equal to infinity it is actually 0. Okay. So and as you reduce r, it goes as a 1 by r behavior, it shows you a 1 by r behavior, some constant times 1 by r behavior. So what we actually see is a behavior which starts at infinity in a manner that is, so if this is 0 energy, 0 on your y axis, this is at infinity the energy contribution due to the first term is 0. So we start at the coinciding with y equal to 0, and then as you come closer and closer and closer, it shows you a 1 by r behavior. So if you just draw this and continue this at r equal to 0, you will see minus infinity. Okay. At r equal to 0, you will reach minus infinity. So that is the contribution of this first term that you see here. This first term here, the contribution of it is that when r equal to 0 it is minus infinity, and when r equals infinity it is 0. So this dotted line here is the contribution of the first term, right. So I will just write here that same term here, minus 1 by 4 pi epsilon naught E square by r. Right. Now let us look at the middle term, b by r power n, which is in this case b by r power 10. It is actually a positive quantity. At r equals infinity it is also 0, so it is also going to start coinciding with the y equal to 0 position, in other words effectively coinciding with the x axis. But because of the r power 10 behavior, even as you decrease r, it initially stays closer and closer to 0. Okay. But when you go very close to 0, it starts increasing in its impact starts increasing, and you see a behavior that is a very steep increase in steep positive contribution by the middle term, which is B by R power 10. Okay, so this is the behavior, and you can easily understand this. So for example, if there is some value of R for both of these terms and you decrease that value of R by a factor of 2, okay, so let us go to half the value of R, then when you go to half the value of R here, the contribution of this term doubles because it is divided by 1 by 2, so it goes up by a factor of 2. Okay, so this goes up by a factor of 2, so from somewhere here it will double the value, right. In the same kind of situation here, when you go from a certain value of R to half the value of R, because it is R power 10, okay, so you are actually going by you are raising the quantity by 2 power 10, so of the order of 1000. Okay, so 1000 is the kind of 1000 times increase or more or even more is what you are bringing about here. Okay, so so this is what you see, right. So so 1000 time increase up here, but there is only a doubling the value in the negative direction. So now these are the 3 contributions, fine. So now what is the total of them, the sum of them, which is that final term that you see there. So when you are at R equals infinity, the only term that is contributing is this constant. So your actual value starts off somewhere here. As you move closer and closer to the origin, initially only the first term is additionally adding to this last term here. Okay, so only this curve is additionally adding to this straight line here, because this one is still remaining very close to 0, fine. So what you see is a behavior that looks like this. It starts getting closer and closer to this second dotted line that we just drew, right. So we start seeing this behavior, but what happens is once you cross a certain threshold, you start seeing this positive value showing up here, which is going up at a rate much faster than this, 1000 times the rate at which that is going down. Okay, so therefore at some value the contribution, the positive contribution from this term is significantly greater than the negative contribution from the other term. So what you see is, you see a behavior that comes down like this and then turns around and goes up. Okay, so this is the curve that we see. Okay, so this straight line that I have drawn here, or this continuous line I should say, not straight line, continuous line that I have drawn here is the sum of the contributions of all of those terms. Each term has been independently identified here. This continuous line is the contribution from all of those terms, right. And this this continuous line now is the energy as a function of position of these 2 ions. As you take sodium and chlorine as 2 independent atoms, and then from that as a starting point you build this crystal. Okay, so as you can imagine, nature tries to attain the lowest energy that it can possibly attain, and this is then the lowest energy that you can attain. Okay, so at this point we have not taken into account the temperature effect on the system. So assuming that this is at 0 Kelvin, this is the position, this is the equilibrium state of this system, or this is the lowest energy of the system, and when I say lowest energy, corresponding to that lowest energy there is a position R0. Okay, so corresponding to the lowest energy of the system, and we will say that we will keep our discussion at this point saying that we are starting this from 0 Kelvin. At the lowest energy of the system there is an equilibrium position corresponding to that lowest energy, which is R0. In other words, if you did reach 0 Kelvin, you will find that the average spacing between all the sodium and chlorine ions present in that ionic crystal would be R0. That is the lowest energy that that system is able to attain, given the fact that there is an ionization energy present in the system, there is electron affinity present in the system, there is Coulombic attraction between those ions, and there is a repulsion between those electron clouds, right. So now this is the composite picture, we have got the complete picture. So and as you can see, we have looked at this system from, in this case this is an electronic contribution to the system, because we are looking at an electron being removed and being added. This is sort of an ionic contribution to the system, because of course it is due to the charges on the ions, but still that attraction is there at an as a two ions attracting each other. So it is a slightly larger scale than what this occurred. then you have a repulsion which is due to electron cloud overlap, okay. So that is again at a subatomic level. So you have a subatomic contribution, you have an electronic contribution, you have a ionic contribution, all of these have come together to show you the picture of that solid of energy as a function of position for that solid, as a function of inter-ionic position in that solid, right. So this is now the picture of what happens in the solid. So what we would now like to see is, given that we have this energy as a function of position, what does it tell us about the impact of raising the temperature of the system, okay. So that is what we would like to understand, because our purpose, as I said, is to understand thermal expansion process, okay. So this is what we are interested in looking at, so we would like to consider this. Now we have R0, corresponding to that we also have an energy E0, okay. R0 and E0 are the two energy levels that we have that we are interested in, fine. So so this is the system. Now let us say we raise the temperature of the system. So when you raise the temperature of the system, what is happening is the atoms are gaining that energy, okay. So when you provide energy to the system, it is not an independent entity, it is that system, in this case that solid. Let us say when you have a wire, you have a strip made out of this particular material. When it raises temperature, when the temperature of it has gone up, when you are able to measure a higher temperature on that system, it means all the atoms present inside it have all also gained that energy in principle, okay. That there will be a distribution and so on, we are only talking of some average. So on average their energy has gone up, right. So originally at equilibrium at T equal to 0 Kelvin, the energy of those atoms was E0, okay. The lowest energy that the system could attain is there. Now we have raised the energy of the system, so it is now having a slightly higher energy level, all the atoms on average are having a higher energy level. So we will just say, for example, that it has an energy level E1, okay, at temperature T1, okay. So we start at T0, we raise the temperature to T1, and so that is the energy level now of the atoms. What does this mean, okay? What is it that we can understand of this system, given that we have now developed this diagram and we are now imposing this additional condition on it that the temperature has gone up and therefore the energy has gone up. What it means is, if you look at this diagram, consistent with this energy, there are two positions that are possible, okay. You could be here or you could be somewhere here, okay. So these are two positions. I mean, if you just draw the horizontal line, if you draw the horizontal line correctly, you will find that there are two positions in this curve where the inter-ionic separation between those ions is such that they have a certain energy associated with them, which is higher than the lowest energy that they could attain. It is a higher energy level, but that energy level is consistent with that temperature, okay. So that temperature corresponds to some energy, that energy corresponds to two values of spacing, okay. So there is a spacing here and there is a inter-ionic spacing here. Those two values of spacing now are able to accommodate this level of energy. So what happens is that the ions now are vibrating, which is something that we mentioned right at the beginning, but the important additional detail that we are now able to say about the system is that they are vibrating between these two positions, okay. So the vibration is occurring like this between these two positions, between the two positions that are consistent with this higher level of energy, right. So that is the thing that we which is now going to give us this insight into thermal expansion process, right. So this is the vibration that is occurring consistent with this new level of energy. You can raise the temperature further, let us say E2, and we can again identify in this curve this position is consistent with this value of E2, this inter-ionic spacing. Similarly somewhere here is the next position that is also consistent with this E2, okay. So again we can draw this okay. So that arrow then indicates the vibration now that is possible. So the amplitude is going up because you can see that initially at 0 Kelvin there was no amplitude, it was stuck at this single position. As you raise the temperature, as you keep raising the temperature, this is the amplitude, this distance that is covered by this curve. So now this is the amplitude you can think of as the amplitude of this, you can associate with these ions. Similarly you can associate this amplitude here, and just to finish off we will just take one more temperature, and with that we will see our next understanding of the system. So three different temperatures I have taken here, T1, T2 and T3, for which the energy values are E1, E2 and E3. Corresponding to them, these are the amplitudes of vibration, and they are all consistent with the all the rules that the solid has followed to form. Okay, all in other words, the kind of to use our term, the model that we have put on the solid, or we believe that the solid is following. Okay, so we have reached this condition. The so far so good. We understand that in this sense it is consistent with our picture that the amplitude goes up as you raise the amplitude of vibration of the ions goes up as you raise the temperature of the system. What is specifically interesting to us is the additional information that we now have, which is the mean position of those atoms, okay, which is not something that we spoke about when we just simply said that the amplitude has gone up. In fact we said that if amplitude goes up and the mean position is the same, there will be no expansion of the solid, right. So if you look at this here, we find that the mean position of this, which is midpoint of this line here, is somewhere here, okay. So somewhere here is the midpoint of this line. If you take this line, somewhere here is the midpoint of this line, and if you take this line, somewhere here is the midpoint of this line. Okay, so this is a hand drawn schematic. If you draw it more to scale, you can see it more clearly. Now if you see, now look at the positions of these points, those midpoints correspond to specific values of r, right. So if you just take this point here, so this is then r1, this is r2, okay, and this is r3, okay. So we have r0 at E0, which is at 0 Kelvin. At temperature T1, energy is E1 and the mean position between the ions is r1. At temperature T2, energy is E2, mean position between the ions is r2. So those are all marked here, okay. And at temperature T3, which is all where T3 is greater than T2, is greater than T1, is greater than T0, which is your 0 Kelvin. So finally at temperature T3, energy is E3 and the corresponding mean position between the ions is R3, alright. So now we have a situation where we are able to see that as you raise the temperature of the system, the mean not only is the vibration amplitude of vibration of the ions going up, we actually find that the mean position at the end as a result of that vibration, the mean position between the ions is actually going up. It is going up from the value that was R0 at T equal to 0 Kelvin. Therefore the solid is now showing an expansion because the mean position between all the ions has gone up from R0 to R3 in this case as you go up from T0 to T3, and since the average spacing has gone up, the overall solid has expanded, okay. So that is the important insight that we get, that for the solid to expand, the average spacing between the ions has to go up, only then the solid will expand, alright. So in fact if you look back at this picture, we see diagrammatically how this has happened, but more importantly if you wish to correlate with all those other information that we have put together in those equations, what we find is that the form of those three terms, okay, the form which is what these dotted lines here are, this dotted line, that is the form of this term here, this dotted line here which is the form of this middle term there, b by r power 10, and the form of this which is a straight line, the last term that is there which is just a constant. It is because of the form of those terms, the way in which those terms actually display their influence in the form of these curves. It is because of that that we end up with a resultant curve which has a shape that we see here. It turns out that because of the way those terms are there, this resultant curve is not symmetric, Okay, so that is the important thing that we wish to highlight. If you see this curve up front, I have drawn it without specifically bringing it out earlier, but you will find that the curve on this side is not symmetric with respect to the curve on this side. If you take any kind of a midpoint, if you take this lowest energy line, if you take for example this R0 line, this dotted line here, you see more region this side than on this side of this of that line. Okay, so this curve is definitely upfront for visual inspection, it is asymmetric. All right, so the expansion process is occurring as a direct result of the fact that this curve is asymmetric. That is a very important piece of information that we are able to now recognize as a result of the understanding that we have built into the system. All right, more specifically, if this curve happened to be symmetric in some hypothetical system, okay, in some hypothetical system, if for example this curve were to be exactly like this, exactly U-shaped curve, if we had in some hypothetical system, okay, and this is at 0 Kelvin. This is only a hypothetical system. In some hypothetical system, if this were exactly symmetric, this part of the curve, if it were exactly symmetric, then what will happen is, even as you raise the temperature to E1 or E2, yes, the amplitude of vibration will go up, but the mean position of the vibration will remain the same. Okay, so that is a very important piece of information to know. The amplitude of vibration goes up, but the mean position remains exactly the same. As a result, this hypothetical material will not show you thermal expansion, whereas this real material where this curve is asymmetric shows you thermal expansion because of this asymmetry present. All right. So in fact, additionally we can also extend this to see that depending on the exact material that you choose, the exact ions and atoms that you choose, the impact, the shape of this curve can change from material to material. Materials where this is a very deep trough, okay, a very deep trough, a very narrow and deep trough will show you a very small coefficient of thermal expansion, because you will have to raise the temperature quite significantly before you see a change in the a reasonably large change in the value of R. In other materials where this is a very shallow but very widely spaced curve, even for small changes in temperature you will see a very large change in the value of R, the mean position. So that is how you explain the difference in coefficient of thermal expansion between materials, okay, based on the kind of bonding that is present in the material, the strength of the bond and so on. So more strongly bonded materials you will find a very deep trough, narrow trough, so that will show you less coefficient of thermal expansion. Materials which are less strongly bonded will show you a much more shallow curve, more widely positioned curve, and that will show you a much greater coefficient of thermal expansion. So this is the general idea that I wanted to cover in today's class. We have seen one property which is very commonly present in many engineering materials, which is used in a lot of engineering situations, which is the thermal expansion coefficient and thermal expansion process. We have understood what thermal expansion is, we have looked at it from a fundamental perspective, we have built a model for the material, and we have looked at it at a subatomic level, at an atomic level and at a macroscopic level, and we have put all these pictures together and now developed an understanding of why or how in a more fundamental sense thermal expansion occurs. Okay. So with this we will conclude today's class. In the next, as I said, this is a class specifically to show you in a single class how this process could occur, how this process, the kinds of detail that we go through to evolve this kind of information. In subsequent classes, when we look at other properties, we may need to develop much more fundamental information to help us reach kinds of models which would give us information or which would give us greater insight into the material, and so that may take a few classes for every property that we are discussing. And so even though it is spread out, if you look back at this class you will get an idea of how it might all fall together. Okay. So with that we will conclude this class. Thank you.